Great, it's recording now. Today we're going to talk about section 4.4, the mean value theorem. The mean value theorem is one of the most important theorems in calculus. We'll look at some of its application at the end of this section. But first, let's start with a special case of the mean value theorem called Rolle's theorem. Rolle's theorem is sometimes mathematicians call it the baby version of the mean value theorem. It's very, very basic version of the mean value theorem. Let's use it as an introduction. Suppose you have a function whose graph looks like this. Look, the function is defined over a closed interval a comma b, and the function evaluated at a give us the same output value as the function evaluated at b. So f of a, f of b, the same level, right? Very good. Now, so you start at this level, at this output value, your output value grows, and eventually your output values start decreasing so that you come back to the original output value, right? Great. Now, notice, if this is happening continuously, right? Continuously, if you go from f of a to f of b, which is the same, right? Continuously, right? No gaps, no holes, no jumps, and also smoothly, it means that the trend eventually has to change, right? From increasing to decreasing. So there is gonna be a point somewhere between A and B where the rate of change must be zero because you are increasing and then decreasing. So rate of change at some point must be zero. And turns out, for example, in this graph is this point, right? The derivative at C, for some C between A and B, should be equal to zero, right? Zero, look, horizontal line, the tangent line. Welcome, Oscar. We just started. We are talking about the mean value theorem, one of the most important theorems in calculus. And we have started explaining this basic version of the mean value theorem called Rolle's theorem. And to put it simple, guys, imagine you are driving a car, right? You are driving a car, and somehow you are getting closer to the highway, you accelerate, and then you decelerate, right? So at a certain point, decelerating, at a certain point, the acceleration has to be zero, right? If you push the accelerator continuously, right? That's kind of the idea. Certain point, zero, to go from positive trend to negative trend, right? Yeah. And you may say, Professor, but that's kind of obvious. Yeah, I agree. It's very natural what is happening here, right? If you are going up, going down continuously, eventually you have to hit rate of change equal to zero, right? To justify this change. Yeah, so, but remember, mathematicians, they're former thinkers, right? So they want to state things and prove them, you know? So, but that's the basic idea. Now, notice this point may appear once, right? Or perhaps twice. Twice, Professor? How come? Well, imagine this other curve, right? Continuous also, smooth, meaning differentiable, is defined over the interval a comma b. Look, f of a, suppose, is equal to f of b, equal, same level, right? And again, right, think about this. You start here at this level, you increase the output values, increase the output values until you reach this peak, right, this mountain. Then the output values, they decrease. Eventually, you're gonna hit this important point, we call them valleys, right? And from decreasing, you change it to increasing again. Here, what happened here once is happening here twice. Look, once here, and also then here, right? The trend is changing, right? Increasing, decreasing. What separates increasing from decreasing is this, right? This point. And at this point, the derivative, we saw this yesterday, remember? Zero, because the tangent line is horizontal, right? But now, since this is not unique, this input value now, let's call it C1. So the derivative at C1, 0. There's going to be another one here, C2, where the tangent line is also horizontal. So the derivative at C2, f prime at C2, also 0, right? 0, 0. Horizontal tangent line. Okay, great, guys. Welcome, Ruyung, CG. We just started. We are talking about the mean value theorem. But first, we are introducing the mean value theorem with this so-called Rolle's theorem, which is kind of a baby version, a very basic version of the mean value theorem, which says that you have a function and the evaluation at the endpoints are the same, right? And the function is continuous and differentiable, smooth. Then, since this is increasing and then after a while this is decreasing, and that is happening continuously, at some point, the rate of change, the instantaneous rate of change, better said, must be 0, right? To go from positive derivative to negative derivative, right? Positive rate of change to negative rate of change. At some point, the derivative must be 0. So, and that happens here at the peak, right? Very good. Now, the theorem guarantees the existence of this real number C between A and B, but does not guarantee its uniqueness. So it could happen perhaps once, but maybe twice, or maybe even 3 times, right? But in this course, guys, we will go up to 2 real numbers that will have this property, right? No more, because we don't want to complicate things, but we just want to make sure that you guys understand that this C that I will show you how to find may not be unique, right? May not be unique. All right, it's called the Rolle's theorem. And it's stated mathematically, it says, if you let f be a continuous function, meaning all in one piece, no gaps, no jumps, right? Connected, right? On the interval a comma b, and differentiable on the interval a comma b, open interval, right? Differential means it's smooth, it's smooth. It's not gonna show corners, it's not gonna show cusps, no sudden turns, right? Then the Rolle's theorem says that there exists C in A comma B, C somewhere in between A and B, such that the derivative at C is equal to 0, right? And that happens right here on the peak, on the mountain here on the mountain, here on the valley, right? Those special points, right? And then you may say, Professor, there's a connection then between what we did yesterday. We talk about local maximum, local minimum, and this, right? I can see here there is some connection. Yes, there is a connection. We will see it later, right? Yeah, great. Okay, so now one exercise related to Rolle's theorem is to verify Rolle's theorem, right? So let's do it together. Verify Rolle's theorem for f of x equal to x squared minus 8x plus 11 on this interval 1,3. But before I go over the Rolle's, this exercise, let me show you this. In our website, I have included this animation that I strongly recommend you to play with. This animation shows a graph, right? And let's say, since we're talking about the Rolle's theorem, let's put it here at the same level, okay? Look, suppose this is f of a, this is f of b. Rolle's theorem says that there should be a point on the graph where the tangent line should be horizontal. That is this, right? You see? It's this. And we said it might not happen once between A and B, maybe happen twice. Where is the second point, Professor? Well, here, right? Just move it here, play around with this animation. Will help you to understand the Rolle's theorem. Look, there you go. That's the other point where the slope of the tangent line is equal to 0, derivative equals 0, right? Here, peak, this is a mountain, this is a valley, right? Good. All right, we will go back to this animation. Again, this animation is on our website, but if you want the straight link, I can give it to you now. It's in our website under course materials, under important or useful links. But if you want it straight, it's there in the chat. Okay, great. So now let's go ahead and verify Rolle's theorem for this polynomial function f of x equal to x squared minus 8x plus 11 on this interval 1, 3, right? All right, let's first verify the conditions for the Rolle's theorem to hold, right, to be true. Rolle's theorem requires continuity. The Rolle's theorem requires that the function must be continuous over this interval, right? So f of x is continuous on the interval 1, 3. Well, this answer should be a yes, right? Because remember, polynomial functions are always continuous when graph, right? The graph of this quadratic function is a parabola, it's all in one piece, so yes, right? Now, f of x, is it differentiable on this interval? And here, yes or no? Maybe I could leave it for you. Anybody on the chat could answer? Can we take the derivative of that function?
Yes.
Yes, very good, Adriana, right? Very good. Yeah, remember the graph of these quadratic functions are parabolas, and parabolas are smooth, meaning they don't show corners, they don't show sudden changes, or they don't show cusps, right? So yes, it's differential, it's smooth, right? Yeah, great. So it means that the Rolle's theorem should hold, right? Should hold. So let's find that C that justifies the Rolle's theorem's conclusion, okay? Yeah, let's find it. All right, so let's do it. We have to verify, in addition to this, that the output values associated to 1 and the output values associated to 3 are the same, right? Well, this guy, no hard to see there, f of 1 will be 1 here times 2, minus 8, minus 7, minus 7 plus 11 is just a 4, right? A 4. And what is f of 3? F of 3, we can compute it in our calculator, right? 3 squared minus 8 times 3. I try to remember this for your homework. I think one of the questions asks you to verify Rolle's theorem. Yeah, this is for 3 and for 1. Yeah, I think the computation here, I missed something. Yeah, both are 5. Yeah, I think it was 2 minus 6 plus 11, 5, right? Very good. Both are 5. Yeah, always, guys, when you cannot compute something in your mind, do it with a calculator to check, right? Yeah, these are 5. So this checks also, right? F of 1 is 5, and F evaluated 3 is also 5. So the 3 conditions for the Rolle's theorems are satisfied. Now, then let's find that C, right, between A and B. Remember, this is gonna work as our A, this is gonna work as our B. Let's find that C between A and B such that the derivative at C is equal to 0. All right. Well, the derivative of this function is equal to 2 times 2, 4x minus derivative of 8x is just 8. And the derivative evaluated at C then should be 4c minus 8, right? 4c minus 8. Okay, so now let's use this. This is supposed to have a solution when I make it equal to 0, right? I make it so 4c equal 8 should show a solution according to Rolle's theorem, right? And that can be verified here, right? Because 4c equal to 8 and c divided both sides by 4 is equal to 2, right? C equal to 2, very good. C equal to 2 is a real number between these two guys, 1 and 3. It's inside, right? It's in there, somewhere in there, such that the derivative evaluated at 2 is equal to 0, right? Look, 2 times 4, 8, 8 minus 8, 0. It checks. So we were able to check Rolle's theorem, right? Indeed, there is a real number such that the derivative eventually is 0 between A and B, which are these two numbers, right? 1 and 3. Very good. Now, let's talk about then the mean value theorem, right? The general version of this Rolle's theorem, the generalization. Okay. A mean value theorem says that if you have a continuous function f defined over a closed interval a comma b, and besides that, your function is smooth, it's differentiable, doesn't show corners, doesn't show cusps, right? It's smooth. On the interval a comma b, open interval, then there is a c in a comma b such that the derivative evaluated at c has to be equal to the average rate of change of the function. Notice this is difference of outputs over difference of inputs over this interval, right? So derivative should be equal to the average rate of change of the function. Professor, can you explain this? Sure. Look, if you are going from A to B now in general, right? F of A is some value, F of B is some other value. They are not the same now, right? Like before in Rolle's theorem, they are just different, for example, right? F of A is this, F of B is this. What this mean value theorem is saying is that if you compute the average rate of change, total change on the output values, which is this, divided by total change on the input values, which is this difference, like this guy, then you're gonna get basically the slope of this line, right? The slope of this line. Oh, draw it for you here. The slope of this line, which we call a secant line, right? Secant line. Secant line. Now, what this theorem is saying is that if you compute the slope of the secant line, which is this, right? This tells you in average what was the change of the outputs per 1 unit on the input values, right? The theorem says that since this curve is all in one piece, continuous and smooth, eventually somewhere in between, you will reach a point whose derivative, whose instantaneous rate of change is equal to the average rate of change. So geometrically speaking, somewhere in between A and B, this is going to happen. All right. Yeah, I think this is good enough. These two guys are going to be parallel, okay? Parallel to this, right? So somewhere there, right? Somewhere there. Not necessarily in the middle. So let me draw this nicely so you don't think that this have to happen right in the middle. So let me just do this nicer. Somewhere, but it will happen. It will happen. Yeah, maybe. This is better. Yeah, I will show you also in the animation how this happens. Yeah, perhaps this is better. Yeah, so somewhere there, right, is going to happen. So somewhere between A and B, there will be a real number C, which is more or less here now, right? C, let's put it in red. C, such that when you go up here, the derivative of the function evaluated at C, which is the slope of this tangent line, will be equal to the slope of the secant line. The secant line, right? 9 below, right? This is this one, right? All right. So you may say, Professor, can you explain this better to mathematical stuff too much? Well, in real life, the way you should think of this is as follows, real world example. Think again about driving a car, okay? Let's say you wake up at 8 a.m., you go to work. For a while, before hitting the highway, you drive a mile. Hit the highway, you start to accelerate. You travel until you reach 6 miles, and then you decelerate, and then you end your trip here at 8:05 a.m., let's say. What this theorem is saying is that since you are accelerating first, and then you are decelerating, and this is happening continuously, right? Imagine you are pushing the accelerator continuously. The theorem says that at a certain point, you must hit the average velocity from this point to this point. So the average velocity, remember, is just the difference, the total difference on the displacement, right? Which is going to be this, right? Let's call it 5 miles, right? 6 minus 1, 5 miles, right? 5 miles over what time? From here to here, 5 minutes, right? 5 minutes. This is the average, right? Velocity. 5 miles over 5 minutes. But remember, if I want to convert these minutes into hours, so I can get something in miles per hour, I have to divide 1 hour here, 60 minutes here. Well, I have to multiply by this factor, right? If you simplify all this in the calculator, right, what this is going to give you is this will cancel with this. 60 gets inverted here. This is 60 miles per hour. 60 miles per hour, right? This was your average velocity from this point when you basically left home, and then you reach the highway, and then when you leave the highway, right? You have to decelerate to leave the highway. 60 miles per hour in average you did, right? So what the theorem is saying is that then somewhere on the highway at certain time, you must have reached this speed, 60 miles per hour, as an instantaneous velocity, right? That's the idea. So again, right? If you draw here a line, this is going to give you more or less the average velocity, right? The theorem says that somewhere in between, you may hit a point where the derivative, the slope of the tangent line, will be equal to the slope of the secant line, right? So that's the whole idea. Yeah, I hope this helps, right? And this is an important theorem because guarantees the existence of that point, right? So somewhere in between, not necessarily in the middle, again, somewhere, this will happen. These two guys will be parallel. Mm-hmm. Yeah. So basically, the point C here perhaps going to be here, right? Look here. We have a point where the driver was driving at 60 miles per hour, right? And then they decelerate. All right. Yeah. So I hope this helps. Okay, but now, guys, our goal is going to be basically to find this real number C, right, between A and B. And we're going to go over different forms so that the conclusion of the theorem should be verified, right? Should be verified. So let's start. Let me show you this example first, and then I will ask you to do something on your own, okay? Suppose they say, this is the worksheet. Suppose they say, find the value or values, right? Remember, it might not be unique, the value C. Find the value or values of C that satisfy the equation f of B minus f of A over B minus A equal f prime of C, right? There's a derivative symbol on top of F. f prime of c in the conclusion of the mean value theorem for the function and interval, okay? So let me do this one, the first one, and then I will ask you to do this one, which is similar, okay? Yeah, so let me do this one. So when they give you this function and they ask you to verify the conclusion of the mean value theorem, you have to, on one hand, compute this, the average rate of change of your function, right? And on the other hand, you have to compute the derivative of the function evaluated at some value c, which we will find, right? You see what they're looking for. All right, so start with this part. Notice that a is going to be -1 here, right? And b is 2, right? So let's compute this, right? F evaluated at 2 minus f evaluated at -1 over 2 minus -1. And let's make that equal to the derivative of this guy evaluated at c. But remember the derivative of f, since f is a polynomial function, x squared plus 3x plus 1, what should be the derivative of this? Anybody could tell us the derivative of this here?
2x plus 3.
2x plus 3, right? Guys, very good, very good. Very good, excellent. 2x plus 3. The derivative of polynomial function 2x plus 3, right? Very good, very excellent. But now I want the derivative evaluated at c. So instead of x, wherever I see x in the derivative, I have to write instead c, right? Like this. So there we have the derivative in terms of c. And here I have some real number I'm going to compute, right? Yeah, so now I'm gonna compute this and make it equal to this. All right, f of 2, what is f of 2? Well, if you take the calculator, since we're working with this function, 2 squared square plus 3 times 2, right? I'm doing this way. In case the numbers are not friendly, you may have to do this, right? Is this 11, right? 11. Great. This is going to go here, 11. Now, after that, we have to compute the other output value, right? So the other output value is the evaluation at -1. -1 here. -1 here. The other value is -1, right? So 11 and -1. Let's write them down. 11 was the evaluation of this, minus the evaluation of this was -1, right? That's the difference of the output values. Difference of the input values are this, minus and minus plus, right? So plus 1, and this one is also plus, right? So 11 plus 1 over 2 plus 1 equal to c plus 3. But what is this guy? 11 plus 1 is just 12. 2 plus 1 is 3, 2c plus 3. And finally, when you divide 3 into 12 is 4, 2c plus 3. Subtracting 3 in each side, you get 2c equal 1, and dividing by 2 both sides, you get that this guy is just 1/2, right? C equal 1/2. So now, guys, before you go ahead and choose your answer, you must verify that this guy 1/2 is indeed inside this interval, -1 and 2. So clearly 1/2 is somewhere inside, right? So yes, you check, and then you take this for your answer. If it's not inside, it means that you didn't find it correctly, right? Must be inside. So notice they're posting two solutions, one solution here. This is the one I have to take, right? I was able to find just one solution, right? But perhaps in some cases we may be able to find two solutions, right? I showed it before, right? All right, guys. So let's start with this basic form, polynomial function, right? And this is the way you find that C that justifies or supports the conclusion of the mean value theorem. Following this, try to do number, I will show you which one you can do now. And little by little, we will go over more complicated forms, right? Mm-hmm. Yeah, great. Yeah, great, great. So, yeah, what's going on there? Mm-hmm. Very good, yeah. So we're gonna go ahead and do this exercise, which is in the bottom here. Mm-hmm. Yeah, very good. This one, can you try this? I think it's slightly easier. Try. Do this. F of x this time is equal to x squared plus 3x plus 4. And you are working in this interval, 1, 2. This is your A, this is your B. And you have to find C such that the conclusion of the mean value theorem holds, right? This. A slope of the secant line equal to a slope of the tangent line, or equivalently, the average rate of change of the function from A to B should be equal to the instantaneous rate of change of the function at some input value C between A and B, right? So follow this. Mm-hmm. Evaluations, right? A is 1, B is 2. Mm-hmm. Try, guys. I will give you time. There are 4 forms, more or less, so we will go over all of them so that you will be okay with your homework and with your exams. Use your calculator. There is a lot of algebra there needed, or a lot of computations, better said. Mm-hmm. Maybe I should write out this part too. Looking to verify this, right? F at 2, always the evaluation at the last endpoint comes first, minus evaluation at the first endpoint over 2 minus 1, right? Yeah, very good. This is what you gotta do. And then on the other side, that derivative, but evaluated at C. Mm-hmm. Yeah, and then you gotta solve for C. Mm-hmm. Mm-hmm. I see students coming out with answers. Oscar, excellent. Very good, very good. Mm-hmm. Very good. Excellent, excellent. Yeah, let's do it step by step so nobody gets lost, right? I have to compute f of 2. F of 2, maybe you can even write here f of 2 first, right? What is that? It's just 2 squared plus 3 times 2 plus 4, right? Using our polynomial function. This is it, right? But this is 2 squared is 4. This is 6. 6 plus 4, 10. 10 plus 4, 14, right? 14. Mm-hmm. Very good. First out. And if you cannot compute it, this doing some mental mathematics, use your calculator. I show you how to do that, right? So this was going to be 1 squared plus 3 times 1 plus 4. 1 squared is 1. 3 times 1, 3. 1 plus 3, 4. 4 plus 4, 8, right? 8, right? Great. Now we are supposed to put that here, substitute that there, right? Very good. So it's going to be 14 minus f evaluated at 1, 8 over 2 minus 1, right? Equal to the derivative evaluated at C. If the function is this, anyone could tell me what's the derivative of this function? Anybody in the chat? Or derivative of x squared plus 3?
2x plus 3.
Mm-hmm. 2x plus 3. Very good, guys. Very good. If you walk away from this calculus course, knowing how to take the derivative of polynomials. Believe it or not, guys, it's very important because in the end, they will show you that any function can be approximated by a polynomial function. And therefore, we can get the derivative of basically anything, at least approximately. All right, great, 2x plus 3. Now, the issue is that we have this derivative in terms of x, but we want the derivative evaluated at c. So it's going to be 2 times c plus 3, right? 2 times c. I substitute 3 instead of x. Great. This is the equation that I have to solve to find c. 4 minus 8 minus 4. 2 minus 1, which is 1, right? But this is 14. Be careful there. So this should be 6. Yeah. What's happened there? Yeah. 14
Professor,
minus 8,
is a
right?
14.
6. Yeah,
no,
14 minus 8, 6. Yeah, very good. 14 minus 8, 6, right? Yeah, very good. 2c plus 3. Yeah, depends. Yeah, great. So 6 here, 2c plus 3. Solving this, right? Solving this, subtracting 3 in both sides, 3 will be equal to 2c, and dividing both sides by 2, 3 halves. 3 halves equal c, right? 3 halves. Notice they have written the answer in exact form, so 3 halves. But before we sing victory, we have to verify that this guy is in reality actually inside this interval, 1, 2. We know that 3 halves is the same as 1.5, right? So indeed, yes, it's inside, right? It's inside somewhere. Not necessarily in the middle, right? It could be anywhere, but it's inside 1.5. So then we check and then we say, this should be our answer, right? Very good, very good. Number 4. Great. Now, this is for polynomials, right? Let's go over the next form. I think the next form is this guy with logs and this guy. Let's go over this form now. Then we will go over the one with natural logs. I'm going to show you this, and then you will do this one, which is very similar, okay? Let me show you this. Suppose they ask you again to figure out the conclusion of the mean value theorem, right? Which is this, f of b minus f of a over b minus a equal derivative at some value c between a and b, right? So they ask you to verify that with a equal 3 and b equal 4. So we go ahead and say f of b, f of 4 minus f of a, f of 3 over 4 minus 3 should be equal to the derivative evaluated at c, right? Now we compute f of 4. What is f of 4? F evaluated at 4, following this function, right, will be 4 plus 12 over 4, right? 12 over 4. We substitute x for 4. But what is this? 4 into 12, 3. 3 plus 4, 7, right? 7. That's f of 4. What is f of 3? F of 3 will be 3 plus 12 divided by 3. This is 3. 3 into 12 is 4. 4 plus 3 is 7. We got the same thing. Well, it's okay. All right, so now we're going to do 7 minus 7 over 4 minus 3. That should be equal to the derivative of the function evaluated at c. But notice, guys, this function f of x can be written this way. X plus 12 multiplied by x raised to minus 1, right? I'm going to put this up here to facilitate the computation of the derivative, okay? So the derivative of that function then should be derivative of x 1, right? Plus 12 multiplied by this guy coming down minus 1, x raised to minus 1, right? You follow it? This. But that has to be evaluated at c. So I'm going to write 1 plus and minus, right? Minus. So let's write minus there once and for all. So minus there should be this minus 12, but no x instead c, right? Because the derivative must be related to c, minus 1, minus 2, minus 2. There we go. Now, good news over here, 7 minus 7, 0, right? 0. So this 0 divided by 1, whole thing 0, right? 0. So the whole thing 0 here. Over here, 1 minus 12. Allow me to write this down here, c squared. Okay, c squared. With positive exponent in the power, right? Now, subtract 1 in both sides. It's a lot of algebra there, guys. Do it any way you're used to solve these equations, right? This problem. Divided by negative 1, 1 equals 12 over c squared. Multiplying both sides of this equation by c squared here, c squared here to eliminate this denominator. Look what happens. C squared times 1c squared equal 12. Taking the square root. When you take the square root, guys, be careful. Plus minus, right? Plus minus the square root of 12. Now, the square root of 12, you learned this in previous courses, is the square root of 4 times 3, right? 4 times 3. A square root of 4 is 2, a square root of 3 here. So I have two candidates for the solution, right? C equal positive 2 square root of 3 and C equal negative 2 square root of 3, right? Two solutions. But now, when you look at the interval says that the solution, whatever it is, should be inside this guy, right? Should be inside this guy, 3,4. So solution should be inside this, right? This interval. This guy is inside, right? This is inside, but this is not, right? You follow, guys? Not inside. Not inside. This one is inside, right? This checks. So you keep just the one that is inside. So this should be your solution in exact form. So it gives you this, right? You follow, guys? Yeah, a lot of algebra there, but since we did the step by step, I hope you will remember, right? So again, average rate of change of the function here, derivative here, you get an equation. Carefully you solve this equation, and then you will end up with a solution. When you get the solutions, make sure that the solution is inside, right? This is positive. Sometimes students ask me, Professor, how do you know that this is between 3 and 4? Look, this guy is 1.73 more or less, right? Multiply by 2. It's not gonna go over 4, right? If you wanna verify it, oh, you can do this. Yeah, always use your tools, guys, when there is doubt. Look, 3.46, no doubt, right? 3.46 is inside. 3.46 is this as a decimal. So definitely is in there, right? Checks. All right, very good, guys. So, so now let's talk about another exercise that you can do on your own. Yeah, we said that this guy was, let me write it here nicely. 2 times the square root of 3, 3.46. 3.46. Definitely is inside, right? Okay. Okay. So now I want you to try this form yourself, right? Take your time. I'm going to give you time, but make sure you master this, guys, because it's going to come out. Homework and the exam that is coming on Friday. Okay, so make sure you can do this. Can you try this? Number 5. 4, 5. Yeah. And as a hint, I will write out here the conclusion of the mean value theorem, right? F of A minus F of B, sorry, minus F of A over B minus A, which is the average rate of change of the function, should be equal to the derivative of the function at some input value C. C between A and B. A in this case is 2. B in this case is 9, right? Some value between. So basically you have to evaluate at 9 first, then subtract the evaluation at 2, then divide by 9 minus 2 here. And then this derivative is the derivative of this. For that, I'm gonna give you this hint. Rewrite f of x as x plus 18. Put this up here, raised to x minus 1. So we can easily compute the derivative, right? Very good. Go ahead. Try. And then probably we will take our first break. And for the evaluations, right, you can use your calculator. You don't have to do every evaluation mentally, you know. Use your calculator if needed. Yeah, maybe we can even write the derivative here, right? The derivative of x is just 1. The derivative of this part will be minus 1 coming down, multiplying 18, minus 18. X raised to minus 1 minus 2, right? That use this derivative. I see someone figure this out for number 5. Adriana, yeah. You made my day, Adriana. Very good. Excellent. Good. Yeah, it's just practice, guys. A lot of algebra there, but if you do it often, work on these exercises, eventually it will look like something natural to do. All right, let's go over this together nicely, slowly, so everybody can follow, okay? So on the left side, I have to compute the average rate of change of the function over this interval from 2 to 9, right? Difference of the outputs on the top, difference of the inputs on the bottom. F of 9, what is that? Let's see. F of 9 is the evaluation of this function at x equal 9, right? So wherever I see x, I substitute 9 instead, right? This. And believe it or not, guys, this is going to be 9 plus 9 into 18 to 11, right? 11. Now, what is f of 2? Instead of x, now I write 2. So I get this. 2 plus 2 into 18 is 9. 2 plus 9, 11 again. So this computation becomes, here is going to be the derivative, right? Yeah, let's write this. This computation becomes 11 f of 9 minus 11 f of 2 over 9 minus 2, right? And this is the derivative. The derivative, I have it here, 1 minus 18 x raised to minus 2, but I'm evaluating my derivative at c, so c raised to negative 2, right? Good news here, 11 minus 11, 0. So this whole thing, 0, right? 0. 0 divided by 7, 7 into 0, 0. over here, I have to solve this little equation. C raised to -2, I will write it as this 1 over c squared. So this will become 18 over c squared, right? C squared. Now I can transpose this over here, changing its sign. I can do many things. And guys here, feel free to solve this equation any way you feel comfortable. With, right? You know, any method you have. So I'm gonna do this. Dividing both sides by -1, I get this. Multiplying both sides of this equation by c squared, I get the following. C squared times 1 is c squared. And here, after canceling these two, 18, right? 18. Time to take square roots in both sides. That's what I'll do next, right? Square root here, square root here. But that comes with a price. You have to attach this plus minus, right? It takes to consider the positive square root and the negative square root of 18. So C becomes plus minus square root of 18. Now, time to remember, guys, stuff that you learned before in algebra, right? 18 can be written as 9 times 2, right? Remember, a square number times some other number. So this can be simplified as C equal plus minus square root of 9 is 3, exact. The square root of 2 is not exact, so just leave it alone. Plus minus 3 times the square root of 2. Now, before singing victory, guys, don't get excited, right? Sometimes you think, oh, but this is the answer. No, you gotta check that this guy, indeed, these two guys, I would say, right? Two guys here. There's a C equal 3 square root of 2 and C equal minus 3 square root of 2, right? You gotta check that these guys are indeed inside this interval. Now, this guy is positive, right? It's positive. And if we calculate its value, in our calculator, 3 times square root of 2 is about 4 point something, you see? But let's calculate. 4.24, right? 4.24. This 4.24 indeed is in there somewhere, right? In between. Not necessarily in the middle, but as long as it is in between, these two values, 2 and 9, you are good. So this one checks. This one is not, because it's a negative number, right? Negative number cannot be inside this positive interval, right? So this one you ignore, not inside, right? Not in 2.9, right? That's why we reject it, right? So you keep this. And that's the one that you have to choose. This. Okay? Excellent. Very good, guys. Very good. Okay, I'm going to show you this number 6, and then probably you can do more polynomials we did. You can do number 9. So let me show you number 6, okay? Natural log of x minus 1. This is natural log of x minus 4. Yeah, very similar. Yes, so let me do this, and then I will continue. Okay, guys, so here we are back into the lecture. Yes, so let's erase this. Okay, we're gonna do this problem now. Separate this. Great. It says function equal to, let's rewrite it here, f of x equal natural log of x minus 1. So we are supposed to verify the conclusion of the mean value theorem, which is that the average value of the function, difference of the output values over difference of the input values, should be equal to the derivative evaluated at some input value c between a equal 2 and b equal 5, right? Somewhere in between. And they want you to find that number, right? All right, so let's do it together, right? So b is 5, so we have to evaluate that 5 first evaluation, then evaluate our function at a, which is 2, then take the difference between the input values 5 minus 2, and that should be equal to the derivative evaluated at c. But if the function is this, anyone could tell me what is the derivative? Hint is going to be like a fraction. But what is the fraction?
It's 1 over 1 divided x.
1 divided by, remember?
X minus 1.
Sarah, you get it. X minus 1. 1, yeah, remember, this is our outside function. This is our inside function. Very good, Sarah. Yeah, but look, Adriana also, no? Right? 1 over this guy, x minus 1, the inside function, right? Times the derivative of the inside function, but the derivative of the inside function is just 1, right? 1. So this ends up being just 1 over x minus 1, as I stated. Yeah, very good. That's the derivative. But this derivative, I have to evaluate it at c, right? C 1 over c minus 1, right? You substitute c wherever you see x in the derivative function. Now that's it. This is going to be your equation that we're going to solve to find our c. Okay, so let's do it carefully. So now you see here, what is f of 5? Let's figure out what is f of 5. F of 5 is natural log of 5 minus 1, right? Natural log of 4, right? Natural log of 4. That's f of 5. F of 2 is natural log of 2 minus 1 equal natural log of 1. Now, you can work with these guys, put them there, or we can work with an approximation. So you choose whatever you want to do here, right? If you want to work with approximations, then you have to get an approximation for this guy and for this guy. Natural log of 4 is approximately equal to ln for 1.386, right? 1.386. Then you have to use that. Now, natural log of 1 is just 0. You will see 0, right? Because e to the 0, 1. You can work with that, or better, for accuracy, right? For accuracy, I would suggest this instead. For accuracy, what if we compute this whole thing once and for all? Look, how? Well, we know that this is natural log of 4 minus natural log of 1 over 5 minus 2 is 3, right? Let's compute this whole thing once and for all, right? So let's try to get the computations such that we minimize the error. So let's compute this whole thing in a calculator. Natural log of 4 minus natural log of 1, which is 0, right? We know, but in case it's something different, this is what you do. When you divide this difference by 3, you get this number, 0.462, right? 0.462. Let's write it down. I rounded it to 3 decimal places. That should be enough. 0.462. So this guy is 0.462 equal 1 over c minus 1. Next, what I'm going to do is I'm going to multiply both sides of this equation, the left side and the right side, by the denominator, c minus 1. C minus 1, c minus 1 here. Here, this will cancel. This will give me just 1 equal to what? This number multiplied by c is 0.462c. Minus this number multiplied by 1 minus 0.462, right? You got it, guys? Yeah. Carefully, so we don't make mistakes. Adding this guy to both sides of the equation, or just transposing that to the other side, changing its sign, whatever you prefer to do, you should get this, right? C equal 1 plus this. 1 plus this is just this. If you don't see that, guys, just use a calculator, it will be right. And finally, dividing both sides of this equation by this guy, 1.462. 0.462 cancels 0.462. This has to be this, right? The same as this 0. Yeah. So this will cancel, and this will be equal to what? 0.662. Let's take the calculator, right? Take your Desmos Scientific calculator, or any scientific calculator you have at hand, right? And then this will be C. C equal this guy, right? Let's see, 1.462 over 0.462. 3.164 rounded to 3 decimal places, 3.165, right? 3.165. Let's write it out. 3.165. 3.165. This is rounded to 3 decimal places, right? That should be enough. Now guys, now before singing victory, remember, we have to make sure that this guy that we have gotten here is indeed inside this interval, right? So inside this interval. Is it inside? 3.165, of course, inside, right? Between 2 and 5, so checks, right? So therefore, this is it. You follow it? Not plus minus, right? No reason to put plus minus, just this guy by itself. Very tricky, right? Look, be careful. All right, guys, so you understood this, right? It's a little bit long, but again, step by step, if you do it, right? Use the calculator for this part, or you prefer, you can get this out. This is 0. You will get something similar. You will be close enough to choose the right answer. Don't worry, okay? All right, so let's check here. We got this. Let's try to do this on your own. This one. Okay, a lot on the homework and also on your exam that is coming up this Friday, okay? F of x equal natural log of x minus 4 is the function. And they want you to find the value of C that makes through the conclusion of the mean value theorem, right? Which says that the average value of a function defined over an interval is equal to the derivative evaluated at some input value C between these two, right? This is our A, this is our B. A5, B9. With those two, get this done, right? Yeah, the derivative of this is gonna be 1 over the outside, well, the derivative outside function is this, right? This is the inside function. So 1 over this guy, the inside function, times the derivative of this, but the derivative is just 1. So take this as your derivative and do the rest, please. Finish this up, guys. Yeah, maybe I could write out that this should be B is 9, right? 9 minus 5, 9 minus 5, and this should be equal to this derivative, but evaluated at C using this, right? Yeah, go ahead. And then on the last part, we'll talk about increasing and decreasing functions. Yeah, see, that comes next. I see some activity on the chat room, which is good. I see some activity. Adriana, awesome. Yeah. Excellent, excellent. Very good, guys. Yeah. Yeah, I know, guys, a lot of algebra, a lot of computations, but it's just the way it is, right? Use the calculator in case, well, in this case, you have to use the calculator. There's no way to compute this using mental mathematics, right? It's a natural log there. Yeah. Yeah, so very good, very good. Yeah, so let's try to do this together, okay? All right, so we have to evaluate somewhere here this guy, f at 9. What is that? Using this function, right? That is natural log of 9, x is substituted with 9 minus 4, which is natural log of 5. And this is just some real number that we can compute. The other one is this, f evaluated at 5, which is natural log of 5, x is 5 now, minus 4 is just 1. So natural log of 1, right? Professor, this is 0. Yeah, we know it's 0. You can write 0 there. But now what I suggest is that instead of writing out this, rounding this, perhaps it's better to put this in exact form, natural log of 5 for f of 9, minus f of 5, natural log of 1, and all divided by 9 minus 5, which is going to be 4, right? And let the calculator compute this, right? Compute this. And so we kind of get this accurately. For the derivative, we said that the derivative of this function is 1 over x minus 4. So the derivative evaluated at c will be 1 over c minus 4, right? C minus 4. That is what goes in the right side here, 1 over c minus 4. Now, let's compute this in our scientific calculator, right? So you may use your Desmos scientific calculator. I strongly recommend you to use this. ln of 5 minus ln of 1, which is 0, right? But what if not? So in general, you should do this, right? I get 0.40235. I'm going to round it to 3 decimal places. 0.402 should be this number rounded to 3 decimal places, right? 0.402. Yes, write it up. So that goes here, 0.402. This is equal to this. Next step, we're going to multiply, and continue here, the left side of this equation and the right side of this equation by the denominator, this way. This times c minus 4, this times c minus 4, right? Very good, very good. So that these two guys will cancel. This will be just 1. 1 here. And on the left side, I have to distribute this multiplication over this difference. I will get 0.402c minus 4 times this. What is that? So let's get it in our calculator. 4 times 0.402, right? I get 1.608. 1.608. Okay. 1.608. All right. Then I'm going to add this guy to both sides of the equation, right? Some students prefer just to transpose to the other side, changing the sign. Feel free to do that, guys. Any method you have to solve these equations should be okay. 1 plus this, 1 plus 1, 2 there, 0.608. And finally, dividing both sides of this equation by this decimal, they should give us the answer, right? 0.402. With a great level of accuracy, I would say. So C equal what? This guy, right? This division. So 2.0 0.608 over 0.402. 6.487, 6.488, right? I would say 6.488. 6.488. 6.488. Now, before we sing victory, guys, remember, we have to check if this guy is inside. Inside, maybe I should write him. And obviously, yes, right? So then we are safe. So you take this as your answer. Pick the one that is closest, right? Closest to this. So for number 945, yeah, I see there's an issue here. Yeah, this is the last digit, doesn't matter, but it's close, you know, that close, right? 48, the two digits, the first digit coincides with this one. You pick the closest, right? You follow, guys? The closest always. Very good, very good. Excellent. Yeah, so we basically have mastered the main forms for this intermediate value theorem. There is one form here that is a little bit tricky. Let me explain this to you, and then we will move on to increasing and decreasing functions, okay? Or maybe you can try this first if you want to try. I will give you some time, and then I will go over this, right? This is just one exercise related to this part. Do this. Again, hint, I'm gonna tell you that the derivative of this tangent inverse is just this, 1 over 1 plus x squared, right? Remember, we gave out a list with the derivative of all inverse trigonometric functions, and in that list, you will find this result. The derivative of tangent inverse is 1 over 1 plus x squared. I think I can show you the list of derivatives. I think it's not this. Let me find it somewhere here. There it is, right? You see it? Derivative of tangent inverse 1 over 1 plus x squared, right? Have these sheets printed out in case you have not memorized them, these results, but this is the derivative. With this derivative, guys, try to do this, right? Try to set the average rate of change of the function equal to the derivative of the function evaluated at some point C, some input value C between -1 and 1, right? This is what the conclusion of the mean value theorem is, right? Yeah. Remember, right? If you are driving, if you accelerate first and then you decelerate, at some point you went through the average velocity, right? Or the average speed at which you were driving, right? That's the whole idea. All right, so let's try to do that, guys. Try to do this. Maybe I should write also this. F at B is 1. F at A minus 1 over B 1 minus 1. Be careful with this, guys. Minus or minus plus, right? Yeah. And this is the derivative. This derivative, you get this from here, right? Yeah. Maybe we can just write it so to facilitate your computation. Yeah, this, right? To solve this for C. Hint, you're gonna be dealing with a C square. So when you take the square roots, make sure you are taking the positive square root, but also the negative square root, right? Both square roots must be considered. And to compute those tangent inverses, use the Desmos scientific calculator, right? Click on function, tangent inverse is there, right? Use this, tangent inverse. For tangent inverse, sometimes students ask me, right, shall I click radians, degrees? Doesn't matter because tangent inverse has as an input a real number, so it does not matter. But however, the output has to be in radians. So for you to get it in radians, I think, yeah, I think you should for the input, doesn't matter, for the output, however it matters. So click on radians, compute this tangent inverse in radians, yeah. In radians, yeah, very good. Yeah, give it a shot, try. You don't have to be right all the time, but probably this is the hardest it could get, right? When it comes to you applications of mean value theorem. And this mean value theorem, guys, let me tell you, is very, very important. It shows that if you deal with changes that are continuous, right, you gotta go through the average always, right? The average, it's something that appears in different fields, like statistics, for example. Right? It seems like nature likes averages. Yeah. All right, guys, let's try to do this together, okay? It's very tricky, but I will help you. So we have to compute f of 1. The first output value should be this f of 1, right? What is this? Well, according to my function is tangent inverse of x. This should be tangent inverse of 1, right? Remember, do not confuse this -1 with exponent. It's tangent inverse. It's arc tangent, right? Tangent, but what is this tangent inverse? Well, if you can use the calculator and get a nice approximation, or you can work also in exact form. The angle whose tangent is 1 is just pi over 4, right? 45 degrees. The calculator probably will show you this in approximated form, right? This in radians, look. This is the pi over 4 that I was telling you, right, about. So you can take this with 3 digits, rounded to 3 decimal places. You can use that. Okay. And then you have to compute this at -1. This, right? And then in the bottom, you have to do this, right? But for the purpose of accuracy, I would say, right, what about working just this way? Look, this guy, yeah, is tangent inverse of, we know that this is pi over 4. This is 45 degrees because the tangent of 45 degrees is 1, right? But let's say, let the computer do, the calculator do this part, right? And this is minus pi over 4. We saw the decimal version of this in the decimal calculator, right? But don't worry, you can do this. Tangent inverse of 1 minus tangent inverse of -1. Let the calculator do this whole thing. 1 minus minus plus, 1 plus 1 is 2. Okay, and this here, 1 over 1 plus c squared. Let the calculator do this work, right? So we click here on fractional form, tangent inverse. Where's tangent inverse, Professor? Here on functions, tangent inverse. Tangent inverse of 1 minus tangent inverse of -1. On the bottom, 1 minus minus 1 or 1 plus 1, right? Same idea. 45, right? 45, but remember, you have to compute this in radians because these guys are supposed to come out in radians, right? So this should be the result of all this whole thing. All right, great. This is it, right? 0.785. 0.785, write it down. 0.785, rounded to 3 decimal places, right? 0.785. This is what goes here, right? 0.785 is the result. Or here 1 over 1 plus c squared. Now we gotta solve this for c squared. For that, remember, we multiply both sides of this equation by whatever we have on the denominator. In this case, is 1 plus c squared. 1 plus c squared. This cancels this. This is just 1. And on the left, I will have this times 1, 0.785, plus 0.785 times c squared, right? Times c squared when you multiply these two guys. Subtract this from both sides of the equation, right? And then you will get that 0.785 c squared is equal to this difference, 1 minus 0.785. This is 0.215, 0.215. Dividing both sides by this amount, you will get that c squared is equal to this, 0.215 divided by 0.785. Taking square roots, remember, you take the positive and the negative square roots, you get this, right? Now, let's see what the number is. Plus, minus. Calculator, square root here of fraction form 0.215 over 0.785. 0.523. 0.523. Positive and negative, right? 0.523, positive and negative. But remember, guys, we have to check that the number that we are choosing is inside this, right? But now, turns out negative 0.523 and 0.523 are both inside, are both in this interval, right? You follow, guys? They are both in there, right? They are both. So this is good, and this is also good. Therefore, the answer that you have to choose is this. Be careful, guys, right? Plus and minus 0.523, right? Follow? Not the one including 0, not the one by itself, positive, but this, plus and minus, both, right? Yeah, very tricky question, guys, but it's the way it is for the application of mean value theorem. Good. So now I think we should talk about increasing and decreasing functions, okay? So we will be able to solve this type of problems first, and then the others in the last worksheet. All right, let's talk about that. Let's go back to the lecture, increasing and decreasing functions. Notice that if you have the graph of a function, for example, this function, recall that if you walk along this function from left to right, which is always the agreement, right? From left to right, notice that here you are increasing. You reach this mountain, this peak, and then after that you are decreasing. You reach this valley, and then after that, from decreasing, you go to increasing again, right? So basically, increasing here, decreasing here, and then increasing again, right? Mathematicians figure out that these trends can be determined by looking at the sign of the derivative. at the sign of the derivative. How come? Well, if your function is increasing, mathematicians figure out that it is because the derivative is positive. And kind of makes sense because remember that the derivative measures the instantaneous rate of change, right? So if the output values are growing, the rate of change has to stay positive, right? Stay positive. At this point, the derivative is 0, but right after, since the output values are diminishing, decreasing, when you take the rate of change, it will be negative, right? So mathematicians figure this out. Derivative here, negative. The function is decreasing because the derivative is negative. And again, increasing again, derivative 0 here, increasing again, derivative positive. So this is the first thing I want you to kind of associate in your mind, right? Increasing, positive derivative, decreasing, negative derivative, increasing again, positive derivative. What happens in between, Professor? Well, if you want to know what happens, here derivative 0, right? Here derivative 0. Or perhaps the derivative here may not exist, right? We talk about that too, right? Could be derivative undefined. But before and after is controlled completely by the sign of the derivative, right? Sign of the derivative. That's the idea. So mathematicians will say that from A to B, this function is increasing, okay? Increasing. Right here. And then again, because the derivative positive, increasing. From B to C, the mathematician will say decreasing because the derivative negative. And from C to D, increasing again, right? Increasing again. Increasing again. Right? And then, moreover, they will say increasing on, and often they will write just A, B open, not close, because remember, for variations, for change, you need more than 1 point, right? Talking about change at 1 point precisely doesn't make sense. For variation, increasing or decreasing, you should consider the open interval, right? Here, decreasing also from B to C, or on B to C, or over B to C, open interval. Increasing again on this interval C to D, right? And again, what happens in between, Professor? In between derivative 0, or perhaps derivative does not exist. So that's the first thing, guys. So formally speaking, mathematicians prove this theorem, right? If the derivative is greater than 0 for all x in this interval, remember, open interval, then f of x is increasing on the closed interval a comma b, right? Yeah. If f prime of x derivative is negative, less than 0 for all x in a comma b, then the function is decreasing on a comma b, right? And I'm gonna even give you a method to figure out this whole trend over the graph of a function, okay? But first I want you to identify when the function is increasing, when the function is decreasing by looking at the graph, okay? I'm gonna do this one and probably show you how to do the next. Suppose they say find the open intervals on which the function is increasing and decreasing, identify the function's local and absolute extreme values, if any, saying where they occur. All right, so turns out this exercise, if they give you the graph of a function, it shouldn't be difficult. It's all about just traveling along the function, right? And seeing the trend as we did here on the example, right? We use green and red there. Let's do the same here. Green for increasing, red for decreasing. So if I start walking along this function, I have to start here and this is gonna be decreasing, right? I reach this valley, I change it to increasing. Increasing. I reach this mountain, change it to decreasing, right? There we go. So I can say that the function is decreasing on the intervals here from -6 to 2, negative 2, right? Increasing and then again decreasing from, I think it's 3 Yeah, let's be careful here. -2 up to -2, -6 up to negative. Yeah, I think it's right here where the whole thing stops. So let's be careful there. Yeah, it's right there. So it should be till -3 then. Yeah, be careful. Yeah, then from 3 here, right? 3 to 6, decreasing again, right? 6, 3 to 6. Now these are disjoint intervals, right? So often mathematicians use the symbol union or the word n, right? Decreasing on this interval and on this interval, right? Great. Now, this is decreasing. What about increasing? Increasing on from here up to here, right? From -3 to 3, right? Yes, from -3 to 3. So increasing on the interval from -3 to 3. We figure out where the function is increasing, where the function is decreasing. But now we have to indicate where is the absolute minimum, where is the absolute maximum. Remember, this is the lowest output value. We call this absolute minimum, right? Absolute mean. And this is the highest output value, right? Highest output value. We call this absolute max, right? So putting together this information with this information, then we should say that increasing on -3,3, decreasing on -3,-3, and 3,6, absolute maximum at 3,3, absolute maximum, right? At 3,3. Absolute minimum at -3,-3. So this is the one we have to pick, right? This one. Follow, guys? Now, can you try this on your own? Just by tracing the graph. This. Try to do this, guys. And then we'll go over a break, okay? The question is, right, figure out where is increasing, where is decreasing, and identify the absolute maximum, absolute minimum, local maximum in case there is local maximum, local minimum, right? So try to figure that out. And the hint again, walk along the graph, use different colors, right? We could use green for increasing, right, perhaps. Then red for decreasing, right? You choose a couple of colors. This might help, right? So figure out where it increases, where it decreases, and also where the function has absolute maximum, absolute minimum, and where it has local maximum, local minimum, if possible, right? If possible, so figure that out. I see. Not that difficult, right? So, Adriana, very good. But wait. I think you have to be careful there with the absolute minimum. I think absolute minimum, absolute maximum. Yeah, yeah, with the absolute, there's something that needs to be adjusted in your answer, Adriana. Yeah, so check that out. It's very close to the one. Let's see. Close again, Adriana. Close again. This is a very tricky question, I think. Yeah, very close, very close. Yeah, but I think absolute maximum, absolute minimum. Yeah, I think this function has an absolute maximum, absolute minimum, but then a local maximum, right? It's a local maximum there. There is a local maximum, yeah. Locally, so one point is the maximum, the highest. Sarah, I think, yeah, I think close also. Yeah, a very tricky question. Ruby, yeah, Ruby, you made my day. Yeah, I think Ruby figured this out. The grays also, right? Yeah, it's very tricky, guys. It's good that we are practicing here because similar questions are going to come up in the exam. Be careful. These choices are very close to each other. Now, Sarah, now correct, Sarah. Very good, very good. Very good that you figure out how to fix this. Yeah, very good, very good. Grace, Ruby. Yeah, but let's do it together so we can go over the second break. When you travel along the function from left to right, left to right, we said, right, agree, right, that up to here increasing, then decreasing, then increasing again, right? Yeah, so it will be increasing on this interval from -2 to 0, right? Zero is here. So from -2 up to 0, increasing. Then decreasing, then increasing again from 2 up to this guy, 4, right? Up to 4. Yeah, 2 to 4. So end here. All right, that's increasing. Decreasing on, look, from 0 to the number 2, right? Great. Yeah, these are the intervals where the function is increasing and decreasing. But now we are supposed to figure out absolute maximum, absolute minimum, relative maximum, relative minimum, right? If they're appear on the graph. First thing, the largest output value, it's clearly this, right? Largest output value here, this one. So this should be definitely our absolute max, right? Absolute max here, right? This point. This is 4,6, right? 4,6. Absolute max. Now, absolute mean here and here. Let me use blue here. Look, here absolute mean the lowest output value, but also here, right? Too. So absolute mean, this point 2,0, but also another absolute mean at -2,0, right? There are two.
So there can be more than one absolute minimum and absolute maximum.
Yes, there could be more than one, Adriana. Yeah, true. Because look, this reached the lowest, right? But also this reached the lowest, right? They're both at 0. Yeah, so there could be more than one.
Yeah, okay.
Yes. Very good. Yeah, that's the tricky part of this, actually, right? Yeah, very good. But now, looking inside, we see that this peak occurs here, this mountain, right? I choose another color, perhaps orange. Yeah, this is a special point too. Look, isn't it true that if you focus on a neighborhood close to the origin, close to 0, then this is a maximum also, right? But it's not the highest of all output values, but it's the highest of all output values around 0, on a neighborhood of 0, right? So this is one of the positions called a local max, or sometimes also called relative maximum, right? Same idea, same word, local and relative, local max at 0,2. Now, looking at the choices, guys, I agree. It's very confusing, but the one that precisely describes this is this, look. Increasing on -2,0 here and 2,4, right? This. Decreasing on 0,2, great. Absolute maximum at 4,6, which is here. Local maximum at 0,2, the local maximum is there. And absolute minimum appears twice, here and here, right? So at -2,0 and at 2,0, right? 2,0. So this is the one. Very, very tricky problem. All right, guys. So mathematicians figure out this nice method I present now that will help you tremendously to figure out when the function is increasing or decreasing. Method to determine a function f of x, where a function f of x is increasing and where it is decreasing. Yeah, it's okay, see, it's okay. Yeah, compute f prime and find the critical points. First, step one, right? We know how to compute the critical points, right, of a function by setting the derivative equal to 0, right? Step two, set critical points on a number line and determine the signs of the derivative f prime of x using test points. Step three, f of x will be increasing over positive intervals, positive between quotations. I will explain to you what that means. And f of x will be decreasing over the negative intervals, between quotations also negative. I will explain to you how that works. All right, so let's start with this example one, which says using the signs of the derivative, find where the function is increasing and where it is decreasing, right? Using intervals. Yeah, probably here between parentheses, using interval, using intervals. Okay, great. So let's do this together, guys. All right, so first step then, we are supposed to figure out the critical numbers, right? The critical number. But for that, we have a method. We know that in order to find our critical numbers, we are supposed to take the derivative, right, of the function first. So let's start by taking the derivative of this function. That derivative is going to be, look, this 3 coming down, multiplying 1/3, 3 over 3, 1. So it will be just 1x squared, right? Square, the derivative of this part. Derivative of this minus 2 comes down, multiplies 2 is a 4. X stays with exponent 1 less. 2 minus 1, 1, right? Plus derivative of 3x, 3. Derivative of 10, 0, 0. So this is the derivative, right? The derivative. Now we set our derivative equal to 0 and solve for x in order to find our critical values, right? Or critical points. All right, so setting this derivative equal to 0 to find critical points, we will get the following. X squared minus 4x plus 3 equal 0, right? Equal 0. We can solve this equation using the quadratic formula, but when factorization is possible, I recommend that you follow factorization, right? It's a little bit quicker. Factoring this, two numbers with multiplication is 3, whose sum is -4. After some trial and error, you will find them 1 and 3, but both must be negative, so the sum is -4, right? So I get this factoring. Now, setting each factor containing the variable x equal to 0, I should be able to find my critical points, right? X equal 1 is one critical point, and x equal 3 is another critical point. You may say at this point, Professor, what about the values of x where the derivative does not exist? Remember, guys, yesterday we explained that if you are dealing with polynomial functions, you don't have to worry about that part, because polynomial functions, the derivative of a polynomial function is a polynomial function as well, right? As you can see. For this polynomial function, x is well defined for any real number. So there is no trouble finding x on the denominator and saying, oh, maybe for this value that derivative may not exist, right? So don't worry about that part. These are the two critical points. That's it. All right, now the method says, right, once you find your critical points, the next step is, and these are critical points, right? Critical points. The next step is set these two critical points on the number line, okay? So you take a number line here and you set these points there. This is a number line. Let's set our points there, right? Okay, so set our points there. So this will be negative infinity. This will be positive infinity. In between, you will have 1 here, let's say, and 3 here, let's say on the right, right? 0 is kind of in the middle, right? Yeah. Or 0 here, perhaps. All right, 1 and 3 set on the number line. Now, these two guys, when set on the number line, they will determine 3 regions. Look, 1, 2, 3, 3 regions, okay? Now, the next task is to determine what are the signs of the derivative over these 3 regions. Over these regions, so we're going to write here signs of f prime of x. This is what we're going to figure out, okay? I will give you a nice technique to figure it out. That the steps or the guidelines that we gave says use test points. Use test point. What do you mean use test point, Professor? Well, for example, here in this region, if you want to figure out what is the sign of your derivative, you can take a test point, number 4, for example, and then evaluate using your calculator your derivative at 4, and figure out if this is positive or negative. If you go to the derivative, which is here, right? Here, the derivative. This is the derivative of your function, right? Okay. And you plug into your derivative the number 4, what do you get? Let's see. 4 squared minus 4 squared minus 4 times 4 plus 3 is equal to 3, a positive number, right? Positive number 3. So let's hold it. And this was 3, positive number 3. So this means that all this sub-interval, let's call it, will have positive derivative, okay? From 3 to infinity, positive derivative. Now let's deal with this other interval, the one in the middle. For that, use a test point. Test point, Professor, yeah, any real number between 1 and 3. For convenience or out of convenience, I'm gonna choose 2, okay? Evaluate your derivative using your calculator at 2 and see if your derivative is positive or negative. I kept this in hold, or on hold, better said, on hold, because I just wanna change the input value, right? I change 4 for the number 2. This is my derivative function. I'm evaluating now at 2, and I get this number -1. -1 as an output value. For the derivative evaluated at 2, this is telling me that the derivative evaluated at 2 is negative, right? -1 here tells me that this is negative. So this negative. All this sub-interval negative derivative. The last one, choose, and again, another test point. Out of convenience, right? Since I can choose any real number between negative infinity and 1, out of convenience, I'm gonna choose 0. Why you choose 0, Professor? Because 0 is easy to evaluate. F evaluated at 0, the derivative evaluated at 0, better said, 0 squared 0, this 0 is just 3, right? 3 here, 3, okay? Positive, right? Positive. Yeah. And I want you to catch this, guys. It's very good to catch patterns, right? Look, I started with a positive derivative, then negative, then positive. They switch, right? They switch. This is a very common thing when you work with the signs of derivative. They switch, especially when the polynomial function is of degree odd, which is the case here, right? Degree 3. You will see this switching. But not always, though, because there are some special polynomials where instead of switching these signs, they repeat. So because of that, to play safe, you should use test points, right? Test points. Okay, great. Now, once we have determined the signs of the derivative, then we can say that over this interval, our function will be increasing here, increasing. Over this interval, our function will be decreasing. And over this interval, our function increasing again. Okay, so basically, as a conclusion, you can say, conclusion, let's write in orange, conclusion. To answer the questions, right, on the worksheet, f of x is increasing where? On this interval from negative infinity up to 1, right? Together, you can write n or the union symbol, 3 to infinity, right? 3 up to infinity. Positive infinity or infinity the same, right? And f of x is decreasing on or over this interval, right? From 1 up to 3, using parentheses, right? Open intervals. Very good, that's it. Okay, so using this nice technique, guys, using the signs of the derivative, we will be able to see where the function is increasing, where the function is decreasing. Yeah, and moreover, let me give you this idea, which is also important. When you do this, notice that more or less the graph of your function should look like this, right? Increasing here, reaches a peak, decreasing here, reaches a peak, increasing here, right? More or less like this, right? I'm not saying this is the graph, but more or less you have this shape, right? This shape. So for you to kind of connect this with what comes later. All right. So now let's go to example 2. Example 2 is a little bit more complicated. So let me make you practice here on this polynomial function first. Where are the worksheets? This thing is below here. Yeah. Practice on this first. This quadratic, easy. Probably we should choose a cubic one. Can you try this? Number 7. Yeah, 6 and 7, 7. Yeah, let's do this. Let's look at 8. Can you try it with the test points? H of z equal 12z minus z cubed. This is the function. Remember, step 1, take the derivative, right? And once you take the derivative, set it equal to 0 to find your critical points. Once you find your critical points, you put them on the number line. You get the 2 sub-intervals, and then using test points, you figure out where the function has positive derivative, where the function has negative derivative, and putting everything together, you should be able to say where the function is increasing, where the function is decreasing, right? Try, guys. And when you solve for derivative equal to 0, probably you should you could factor, right? But also sometimes it is better to isolate the variable. I will show you when we go over this. And if 0 is available for you to use it as a test point, if it's available, use it, because evaluation at 0 easy, right, to compute. Mhm. Okay, guys, let's work this out together, okay, so we can see other forms. First, we are supposed to take the derivative. If we take the derivative of this function, derivative of 12z is just 12 minus derivative of z cubed, 3 comes down, z stays with one less on the as exponent, right? 3z squared. This is the derivative. I see someone figure this out. Adriana, yeah, excellent. Very good, Adriana, very good. Yeah, you got it, Good work, yeah. So we are headed there. Derivative is this, right? Now I have to set my derivative equal to 0 and solve for the variable, which is in this case z, right? So I gotta do this. 0, solve for z. Now, factorization is possible, but let me show another strategy. Let me isolate the variable. Oscar also, you got it, Oscar. Very good, Oscar. Very good. Excellent. Yeah, so let me choose this other strategy. Let's isolate the variable because there's just one z there, which is a square. Let's just subtract 12 in both sides. Look at this, right? For the sake of variety. You can try factorization as well. It's equivalent. So dividing by -3 both. I get a z squared equal -3 into -12 is +4. And taking the square roots, let's do it here. Z squared equal 4. Taking square roots, the square root positive negative of 4 will be equal to z, right? Positive square root is 2. The negative square root is -2. So z is equal to 2. Z equal -2 are the critical points, right? Are the critical points. Okay, now with these critical points, our method suggests, okay, take your critical points, set them on a number line, right? Number line in the middle 0, 2 should be here on the right, negative, and 2 positive on the negative to the left, positive to the right. Here infinity positive, here minus infinity, right? These two critical points determine subintervals on the number line, right? Subintervals, this, and this, 3 subintervals. Now, the trick is to figure out what are the signs of the derivative over these subintervals, right? You may start anyway, in any subinterval. I choose always the last one, this one on the right. If you start here and you want to figure out the sign over this subinterval, choose a test point. Anyone could tell me what would be a good test point for this region, for this part?
3.
3. Excellent, Adriana. 3, right? 3, right? It could be 4, it could be 5. Yeah, but 3 is the closest, so makes sense. Get the derivative, evaluate at 3, and see if this is positive or negative. If we evaluate our derivative, this function, right, at 3, what do we get? Let's check. We are gonna get there 12 minus 3 multiplied by 3 squared, right? 3 squared. It gives you minus 15, which is a negative number, right? Minus 15. So let's write it here, minus 15. Minus 15, right? Minus 15. So minus 15, great. Negative, right? Negative. So this is negative. Now, this guy in the middle, let's figure out what it is. For that, what test point do you think we should take for this test point for the one in the middle? Anybody? What test point do you think we should take?
0.
0. Very good. 0, right? 0 is the most convenient number when it comes to evaluations, right? So if you put 0 here, this will be 0. we have to do it on the derivative right here. If this is 0, 0, so 12 will be the evaluation, right? Evaluating our derivative, this at 0 is just 12. Positive, right? Positive. Plus. And over here, what could be a good test point for this part? Anybody? What test point should we use here? H prime at
-3.
-3, right? -3. Good, good, Ariana. -3, right? Now, notice if you put -3 here, it's the same as putting 3 because the square in -3, square in 3 is the same, right? It's same. So you will get the same output value, -15, right? You can check in the calculator, minus. So this means that all this region minus negative. So this is telling us that over here, this function should be decreasing from -2 to 2, increasing, right? Because the derivative is negative. And from 2 to infinity, it should be increasing, decreasing again, right? Decreasing again. All right. So then it means that we have to choose the one that is saying increasing on -2/2. Let's put this with a color here. Look, this is increasing right here. Then decreasing over these two intervals, right? Over here and here. You follow, guys? Decreasing here, but also here, right? Decrease. So here and here, right? Very good. So that's it, right? This is the answer. Follow, guys? Yeah, so now you may say, Professor, they're using brackets, they're not using parentheses. It's okay, because remember at one point, precisely at one point, it doesn't make sense to say that the function is increasing or decreasing, right? It's over interval where it makes sense. So don't worry about these brackets or parentheses here. It's the same. Very good. All right, that was this. Now let me show you how to deal with these special cases, okay? And then probably we'll go over another one of this is similar, so you can do it at home, but this type of thing, right? Rational functions. Yeah, this should be easy too, but rational functions, right? So let me give you an example and then we'll go back to that. All right, so if we go back to our lecture here, I think I had one example here. Yeah, this. Using the signs of the derivative, figure out where this function is increasing and where this function is decreasing. The function is given by this formula, f of x equal -8 over x squared plus 3, okay? Now, first thing I'm gonna do is, since I have to work with the derivative of this function, I have to take the derivative, right? Allow me to rewrite this function as follows. -8 times, allow me to put this up here. X squared plus 3 raised to -1. So I can use the chain rule, right? The other option is to use the quotient rule, but probably it's more complicated, right? So I'm gonna just rewrite this way so I can use the chain rule, right? Okay. So now, if I take the derivative now of this function, what that will be? Well, notice this constant 8 will come out. This is gonna be my outside function. And this will be my inside function, right? X squared plus 3, x squared plus 3, very good. X squared plus 3, my inside function. When you take the derivative, start with this. The constant -8 comes outside. Derivative of the outside function is -1 coming down. You stay with 1 less here, right? -1, which is going to be -2. Keep the inside function here, x squared plus 3, and multiply this by the derivative of this inside function. The derivative of this inside function is derivative of x squared twice x, right? Twice x. So that's it, twice x here. This is the derivative, right? Let's write this out nicely so we can use this to get the sign. Negative times negative, positive, right? Positive. +8. And +8 times 2, 16, right? 16x. Now, this guy is this, right? X squared plus 3 raised to negative 2. Put this down. So for presentation purposes, right? And this should be 16 times x over x squared plus 3 raised to the second power, right? Believe it or not, guys, this is our derivative, right? This is our derivative. This is how it looks like. Very good. Now, the next step is to set our derivative equal to 0, right? Equal to 0 and solve for x to find our critical points. So we set this guy 16x over x squared plus 3 squared equals 0, right? Notice that this guy goes to the other side multiplying. Equivalently, if you multiply left side and right side of this equation by x squared plus 3 squared, this is what you get, right? 0 here, right? 0. And here, these two cancel, 16x equals 0, which tells us that x must be 0, right? X must be 0. Once you divide by 16 both sides, x equals 0. So, I got a critical point there, right? Now, you may say, Professor, but now you have to check if the derivative function is undefined for some value of x. But look at this nice denominator, x squared plus 3. This x squared plus 3 is never 0, right? I'm going to write this as a note. So if you want to kind of understand where this comes from, note x squared is greater or equal than 0 if you add 3 to both sides of this equation, x squared plus 3 greater or equal to 0. So there's no way for this to be 0, right? This to be 0 equal than 3 here, right? So no way for this to be 0. So don't worry about that. Just stay with this as your critical point, right? That's the whole idea here. Yeah. All right. So there we go. 3 this here, 3. Yeah. Okay, great. So now we are going to go to the number line, right? Number line. And we're going to set our critical point 0 on the number line. There is just one critical point 0, right? So this critical point will subdivide our line into 2 sub-intervals, right? Next, we have to find or figure out the signs of our derivative on this or over these 2 sub-intervals, right? Let's start here. Test point for the right side. Out of convenience, I can choose the test point to be 1. Evaluate your derivative as your test point 1 and see if this is positive or negative. The derivative is this, right? This evaluated at 1, of course, is positive. But let's calculate it, right? So say 16 times, what really matters is really the sign, right, at this point. Divided by 1 squared plus 3, all squared, 1, right? The whole thing 1. Positive, right? Positive. 1 positive. So what matters? Positive is the derivative here. Over here, notice that this negative 1 squared will be the same, but this will be negative 1, right? So if you choose test point negative 1 now, the derivative at this point will be negative 16 here. 1 plus 3, 4, 4 squared 16, 16 into negative 16, negative 1, right? So this should be negative. So what this is saying is that from negative infinity to negative 1, decreasing, and from 1 to positive infinity, which lives here, increasing because derivative positive, right? Increasing, following the theorem. All right, so decreasing, increasing. So that is what you conclude. Then the conclusion should be, conclusion, f of x is increasing on this interval, right? From 0 to infinity. F of x is decreasing on or over negative infinity up to 0, right? Up to 0. That's it. Okay, guys. So following this idea, try to go over this exercise on the worksheet. I will show you now. I think it was here on the bottom. So we just have to be careful when taking the derivative, right? And then probably we will visit other one of those. Can you try this with rational functions? Huh? Yeah, this is the derivative. No, this is the function. So h of t equal 1 over t squared plus 1, right? And they ask you find where h of t is increasing and where h of t is decreasing by looking at the derivative, right, and finding the critical points. Yeah, so do that, guys. So compute the derivative, but hint, you can try what I did before, right? Rewrite this function as this. T squared plus 1 raised to minus 1. So you can use the chain rule, right? The chain rule with this outside function and with this inside function. So take the derivative next. Then figure out the signs of this. Yeah, go ahead. And tell us if you figure out the answer, right? Where this function should be increasing, where this function should be decreasing. I see. So the students figure this out. Let me check. Adriana, very good, excellent, very good. Yeah, Oscar also, very good, excellent, guys. Yeah, once you take the derivative, it shouldn't be hard, right, to figure this out. Yeah, also Grace, very good, Grace, very good, excellent. Yeah, very good, guys. So let's do it together. It all starts by taking the derivative. When this rational function is written in this form, it is easy to take the derivative using the chain rule, right? Remember, the derivative of outside function should be this exponent coming down, and here minus 1, right? One less. You keep the inside function here for a moment, right? T squared plus 1, and you multiply here by the derivative of this inside function. Derivative of t squared is just 2t, right? 2t, great. Very good. Now, simplifying this, you will get that the h prime of t should be negative 1 times 2, negative 2, right? Negative 2 t, don't forget the t there, there's a t there, so negative 2t over this t squared plus 1, right? T squared plus 1. This raised to, it should be negative 2, but since you put it down, it should be raised to a second power, right? Yeah, I don't want to confuse anyone. This was this times t squared plus 1 raised to negative 2. We just put this down, it's this. All right, but then when you set this equal to 0, set h prime of t equals 0, what's going to happen? Minus 2t over t squared plus 1 squared equals 0. Multiplying both sides of this equation by this guy, we will get rid of this guy, right? And this will be 0. Right, so t squared plus 1 here is squared, t squared plus 1 is squared, 0 here, over here, this cancels with this, minus 2t. At this point, dividing both sides by negative 2, we get that t is equal to 0. T equals 0. Great. This is my critical point. But now I have to ask myself, right? Is there a way for the derivative b to be undefined, knowing that this is my derivative? When you look at the denominator, we see that the denominator is super nice. It's t squared plus 1. T squared is greater or equal than 0. If you add 1 to both sides of this inequality, this tells you that t squared plus 1 is at least 1. It will never be 0. So we are safe. This denominator will never be 0. So this is the only critical point, right? So we set our critical point now here in the middle. This will determine these two subintervals. We choose cleverly test points. I'm going to choose test point 1 here, and you evaluate your derivative at 1, right? This is all about figuring out the signs of your derivative here, right? H prime of t. For test point 1, the derivative of the function h, let's be proper, this is h, should be equal to what? Well, let's see, h here. This derivative should be equal to 1 substituted into the derivative into here. Look, 1 squared is 1 plus 1, 2, 2 squared 4, negative 2 times 1, negative 2, negative 2 over 4, negative 1/2, right? Negative 1/2. So this one, negative 0.5. And guys, I did this mentally, right? If you cannot do that, again, guys, play safe. I just take the calculator, right? And just put it there. When you do your homework, perhaps the values that you have to deal with might not be as friendly as this ones, right? So then use your calculator there. Plus 1 is square, right? Indeed, negative 1/2, right? And now for this side, I'm going to use another test point. I'm going to use test point negative 1. But notice that the evaluation the new evaluation should be this, right? Make sure you put parentheses here to evaluate negative numbers. So negative 1 should be placed inside parentheses. Look, the new evaluation 0.5, okay? So for negative 1, the evaluation 0.5. So if you use the test point here, negative 1, here, since this is negative, this whole thing was negative, right? So negative here, less than 0, negative. Yeah, but now this one is h prime negative 1. Remember, we got this to be positive, right? Positive 0.5. This is positive, so this whole sub-interval positive. It means that increasing here increasing here, decreasing here, right? Decreasing here. All right, so increasing from negative infinity to 0, decreasing from 0 to infinity, right? And this is what this guy is saying, right? Increasing from negative infinity to 0, decreasing from 0 to infinity. Very good, guys. That's it. Okay, so now let's see if we can finish with one more exercise here. Let's see. Yeah, so rational function we are covered. I want to warn you about this. Yeah, this was all about finding where the function is increasing, where the function is decreasing, right? So easy. But these other questions, often students ask me. For example, this 1, 2, and 3. You gotta be careful there because notice the question is asking you, find the largest. So I'm gonna highlight this, find the largest open interval where the function is changing as requested. Largest open interval where the function is increasing, okay? Largest open interval here where the function is increasing. Largest open interval where the function is increasing, right? The largest. There might be 2, right? Perhaps, who knows? So in order to clarify this, probably I should do explain to you number, the one that gives always trouble is I think number 2. All right, I will show this to you quickly. This is easy as a parabola, you will handle it, right? Just the largest open interval where the function is increasing. Okay, let's try to do this. This function is a composite function. Let me rewrite it here. Y equal x squared minus 9 squared, right? Composite function. Why you say that, Professor? Well, because here you see clearly the outside function and here the inside function, right? It's a function evaluated inside or into another function. Yeah, the inside function, outside function. So we'll all start by taking the derivative, right? To find the critical point. Derivative here, outside function has this derivative. 1 less here, 1 here, we will disappear, right? You don't have to write it. Here inside function, x squared minus 9 times the derivative of the inside function, but the derivative of this inside function is just twice x, right? Twice x. Rewrite this nicely. Simplify 2 times 2, 4, x times x squared minus 9. Yeah, this is the derivative, right? X squared minus 9. This is the derivative. Now, we're gonna set this equal to 0. Set your derivative equal to 0. And we have to find our critical points. So we're gonna set 4x times x squared minus 9 equal to 0. We're gonna solve for x and find our critical points. This factors as x minus 3 times x plus 3. And then setting each factor containing the variable equal to 0. We got the following, right? First critical point will be this, x equals 0. From here, right? First critical point. Second critical point from x minus 3 equals 0. Clearly, x should be equal to 3. Third critical point from x plus 3 equals 0. Subtracting 3 in both sides, x equal minus 3, right? So these are my 3 critical points. Now, what is next? You are supposed to put these critical points on the number line, right? On the number line. This way, 0 in the middle always, right? Negative 3 should be on the left of 0. Positive 3 should be on the right of 0. These 3 critical points will determine subintervals here, right? Subintervals. Yeah. And then using test points, you're supposed to figure out the sign of these 4 subintervals. Now 4. So starting here, I can choose this test point 4 and evaluating my derivative y prime at 4. I have to see if this is positive or negative, right? Look, if you put inside your derivative the number 4, notice that that's going to be equal to what? Let's calculate it, right? 4 times 4 times 4 squared minus 9, 112 positive number, right? 112 positive number. So this guy positive, 112 positive. Very good. So this guy positive, right? So let's just move here. Yeah, great. And see, this is really minus this point, positive, 112. All right, so all this positive. Now here I choose another test point, for example, 1. Evaluate y prime at 1. If this is 1, this is going to be 1 minus 9 negative. This part is positive, so the whole thing will be negative, right? So negative. Negative this one, negative here. And if you want to calculate it, you can do that too. Just substitute instead of this 1. And you can even get the exact value, right? But again, it's just a matter of getting the sign. Negative 32, negative, right? Negative. All right, great. So negative less than 0, right? Negative 32. So this negative. This guy, take another test point out of convenience, negative 1. I'm choosing negative 1 because look, this negative 1 evaluated here will be 1 minus 9, 1 minus 9 minus 8. And this will be negative now. Negative and negative now positive, right? Same output, but positive. So this will be positive. Positive here. All right, positive here. Positive. Same output, but positive, right? That's positive. And finally, this, I choose cleverly again, negative 4. Let's say negative 4. That's critical point. When I do the evaluation, this will be the same as evaluating 4, right? Notice, but since it's negative, this will make it negative, so minus 112, right? This evaluation, y prime and negative 4, negative. So this negative. Yeah, great. So now, what is important is to notice that this is going to be decreasing here, increasing here, decreasing here, and increasing again here, right? But now, being careful, which is the largest interval in your opinion such that this function is increasing? What's the largest? Anybody could tell?
4, the 3, the 1, 1, 2.
Yeah, increasing, yeah, good, because look, increasing where? It's increasing here, just highlight. Here, but also here, right? So the largest will be from 3 to infinity, right? You follow, guys? 3 to infinity, right? The largest. You say, Professor, but also increasing here, but largest. This is larger than this, right? This is an infinite interval. This is a bounded interval, right? Maybe I should write another largest. Right? Largest, this one. So this is the one that you choose, right? You follow, guys? So don't be surprised there. Yeah. Okay, so with this, I think we should finish, right? This is the answer.